I attempted to put the lecture up on LMS, and one of the reasons I was late today was that it was loading for over 20 minutes, and then I actually just gave up. So I will attempt to load it up. If anybody knows how to load 1.6 gig files into LMS, I would appreciate your feedback.
Go to the help desk and use their gigabit connection.
Oh, that's a possibility. Okay, good. All right, so back to this. That's the potential at some point in space due to a charge, right? And I'll just write the other relationship here. The electric field, that's the one that tells us what the forces are, is minus the gradient of that potential. All right? And that's the potential for a point charge, but I can just, you can very easily see that if I just have a whole bunch of other point charges, I just have to add those in order to find the total potential due to all of the point charges. Right? So the potential due to many point charges at some position r would be equal to the sum over all the charges, each of the charges divided by r minus ri. Now I've written these vectors in there, but this is really just a distance. Remember, it's x minus xi squared plus y minus yi squared plus z minus zi squared in Cartesian coordinates, square root, right? So that very frequently is a very easy thing to calculate, just calculating a distance and not worrying about adding in vector directions. And if I have a continuous distribution of charge, then I would integrate over some primed volume, dv prime, rho r prime, that's where the charge is, r minus r prime. That's it. Okay, again, that given a charge distribution, it's really easy to calculate the potential at any particular point in space. It's just a very short computer program where you just got to specify where the charges are. Very frequently, because this arithmetic is much easier than the vector arithmetic and calculating the field, it's easier to calculate the potential and then take the gradient of the potential in order to find the field. Right? So now you've got an additional way to ask yourself, how do I want to solve this problem? So given a problem, you look at it and you say, does it have a lot of symmetry? Can I calculate the field using Gauss's law? If not, or actually the real question is this one of the problems that he's shown me? Because those are the only ones for which Gauss's law works, right? So does it have sufficient symmetry? Is it one that I've seen? If not, then you might have to actually do the integral to find the field. You will have to do an integral. No, you won't. There's going to be another way. But you might have to do the integral to find the field. And then the next question is it easier to calculate the potential, which now you have to calculate as a function of position. And once you've calculated potential as a function of position, you take the gradient. All right? Or if you're being asked for the field at one point, if you're being asked at one point, then sometimes it's easier just to add up all the vector fields. But if you're being asked for the field as a function of position, then you might as well find the potential as a function of position and take the gradient. Does that make sense? Okay, to some of you at least. The CGS unit for this thing, this potential here, is the stat volt. Which is 1 erg per ESU, which is approximately equal to, no, it's not approximate. Oh, it's always approximate.
Yes.
300 volts. It's actually 2.9998 or something like that. 299.8. Whatever the speed of light is.
299.792.458.
Whatever. Yeah.
And of course you have that memorized.
Okay. Yeah, okay. Let me do one example. It's all on video, so I can erase. All right, let's find the potential and the field due to a uniform disk approach. All right? Yeah. Yes. So there's my disk. I'll call it radius r. I'm going to go up some distance z above the disk. We could do this, I mean, we could write this out quite easily, but then the integral becomes quite complicated. If we don't do it on the axis, I'm going to do it on the axis. Probably give it to you for homework off the axis.
Thank
I don't
you oh
remember
so
what I
much.
gave you. What?
Thank you oh so much.
Okay. Actually, I think the problem that I gave you for homework, and it is doable, is the potential as a function of position above, or actually anywhere around a square of charge.
I did that already.
So we've got a disk here, right? And we're going to calculate the potential first because figuring out the field includes vector directions, and I don't want to have to think about those. All right. So I asked if I have a little bit of charge over here, dq prime, then what field? What potential does that lead to? And my distance here, I think I'm going to call distance from the center. I'll call r prime. And height, I got z. So I only need that distance there. I won't write it down. Okay. A little bit of charge out here, I'm going to write as r prime dr prime d phi prime. That's my element of area times sigma. Okay? And I can make life a little bit easier for myself still because I realize that everything around this circle is at the same distance. So I'll have a different dq, let's call it dq prime, which is all that charge around a ring. Okay? And so that's sigma times, all right, 2 pi sigma r prime dr prime. Okay?
Mm-hmm.
Okay. Then, I want to find the potential due to that. And that's the integral of rho over r minus r prime dv prime over the prime region, right? My z-axis is a delta function, and so now I just have to do the area integral, and so that's going to look like sigma 2 pi sigma integral r prime dr prime over the distance, which is r prime squared plus z squared to the 1/2. Okay? And so that's an easy integral to do. I do this from 0 to capital R. And if I look it up correctly in Chows, I encountered a situation yesterday in Physics 2. It was a regular Physics 2 problem where where the student went to look it up using Wolfram Alpha, and Wolfram Alpha said, timed out. It was actually this one exactly, right? Timeout. And while she was inputting it into Wolfram Alpha, I pulled out my Shounds, and I looked it up and got the answer faster than she could with Wolfram Alpha. So the old ways can sometimes still be good. So that's it. Do the integral, that's what it comes out to be, I hope. All right? Now if I want the electric field, I just take the gradient of the potential. And when I do that, I end up with, there's only z, there's no other functions in here, so it turns out the only derivative in z has any meaning, which is good. We knew by symmetry that it was going to have to be that way along the axis, but we see that it's only a function of z, so that's the only derivative that's going to remain in the gradient. So that becomes 2 pi sigma z hat by z, and you guys could do that derivative better than I can. No, I'll write it out. Minus 2 pi sigma z hat times z times z squared plus r squared to the minus 1 half minus 1. I sort of expected that minus sign to go away, but it hasn't. I'm going to leave it that way, and you are going to fix it. You'll just trust and believe me. Okay, yes. Did you intend that to point that way?
Yes.
Yeah.
That was during your irrelevant aside.
Oh, okay. You had a question? No.
Turned out to be wrong.
Okay. Questions can't be wrong. They could just be stupid. There are no stupid questions. Only stupid students. Okay.
Approve.
We can ask, though, we should always ask, is this reasonable? Is this okay? So we ask as z goes to 0, as we go into the plane of this guy here, then this thing should reduce to the Gauss's law example, all right? When you get really close to a very big charge distribution, we better get something like 2 sigma or whatever the answer came out to be
2 pi
for
sigma.
Gauss's law, all right? What?
2 pi sigma.
Was there a pi in there? I don't remember. Yeah, probably. 2 pi sigma? No, there was a 4 pi. Yeah,
2 pi sigma.
right, okay. So we should get an answer that looks like that, right? So we can look, ooh!
Yeah.
It works. I go to 0 and this becomes 2 pi sigma. So probably that minus sign belongs there,
Yes.
right? And then I can ask, as z goes to infinity, what happens? And as z goes to infinity, this thing's going to look like point charge. Total charge, 2 pi sigma times pi r squared. Actually, pi r squared. Z goes to infinity. This goes to 0. This becomes 1.
No, that
No,
goes
no.
to 1.
This goes to
1.
1 minus 1, so it goes to 0. So if I really want to do this to figure out whether it's going to work or not, because this actually goes to 0 as it should, but I want to find out how it goes to 0, probably the best thing to do here would be to Taylor expand this expression and then find out what the next term out is. Okay? So the Taylor expansion, go over here, z times z squared plus r squared to the minus 1 half. That, right, is approximately equal to 1 minus 1 half r squared over z squared. Right? And 1 minus 1/2 r squared over z squared. The 1 cancels out. I'm just left with r squared over z squared. Pi r squared times sigma is the total charge. And so I'm left, I just get a 2 here. 2 q over z squared. Uh-oh. 1/2.
Yeah.
So q over z squared. Yes. All right? So that worked in the 2 limits, which means it must be right.
You think?
Okay. So, you're going to have a homework problem on the next thing that I'm going to talk about, so I better rush to it. I better get to it. It's in the notes. I'm posting the notes, and I'm sorry I've entertained myself too much and run out of time. But
Hey, we enjoyed it.
all of this, all of what I said before, returns me to how to calculate the potential. Right? And I've got del squared phi is equal to 0 in regions where there's no charge, Laplace's equation. Okay? And I have a whole page here on demonstrating the uniqueness of a solution to this problem, which basically says that, so I'm just going to state it. If you find a solution to a problem that satisfies a set of boundary conditions, so you just find a phi, and if I have no net charge in the region that I'm solving, you find a phi that satisfies boundary conditions. This is the boundary condition. Then you have found the potential. However you get it, if you find something that satisfies the boundary conditions, oh, and Laplace's equation. So a solution to Laplace's equation that satisfies the boundary conditions, you're done. Okay? So it comes down to, so for example, I might have a problem where I set the potential at this surface equal to 1, and I set the potential over here equal to 0, and I set the other surfaces equal to 0. Now I know the value of the potential on the boundaries. Once I know that, the solutions, I could write down all of the possible solutions to the most general set of solutions to Laplace's equation. Find that sum of set of solutions that gives me the proper boundary condition, and I found the solution. Okay? We're going to spend all of next class actually doing that. But the other consequences of Laplace's equation and uniqueness are that, and again, I probably should, and I might come back next class, I probably will come back next class and be a little bit more careful about this, but I want you to have the useful facts for now. That says that the potential cannot have an extremum in the charge-free region. Just look at derivatives. Can't. Derivatives are 0. Everywhere. Right? You can't have an extremum. Right? All the extrema have to occur on the edges of the regions, or the smallest and the largest point. For example, just like there, the extrema have to occur in the median. There aren't going to be any inflection points. Well, there can be inflection points, but no, maybe there can't be inflection points. There can't be extrema in that region. Let's look at that. They must occur at the boundaries, right? And a consequence of that, there's uniqueness. I will go through uniqueness, is what's called the mean value theorem. And this is really cool. The mean value theorem says that the value of the potential in the center of a region, in some region, is equal to the average of the potential on the surface of a sphere surrounding that region. Okay, well, surface of a sphere, heck, what do you do with that? Well, there's an approximation that we can make here, which is that, let's say I've got a problem where I set the potential on some surface equal to some value. And then over here, I set the potential on this surface equal to some value. Right? Then, at every point in here, you can look at the point, and I can say that the value at that point must be the average of all the points that surround it. Right? I should do it on surface of a sphere, but I'm going to do it in an approximation where the points are very, very close together. And I'll just make it into a, in this particular case, a rectangular grid. And then I say, okay, if I know the potential here, 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 and here, I can figure out what the potential is in the middle, approximately. Okay? So, what you actually do is that you know the potential at these points here. You just make a computational grid. You guess some set of initial values for inside in here. So for example, I might guess 0 for the potential everywhere inside. I know it's not, but I guess it. Right? Then I go to this point, and I calculate, given all the points around it, I calculate what the corrected potential would be given what I know the points around it to be. So it would be 0, 0, 0, V1, 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 V1. Right? Actually, it's just going to be these 4 points, not those. Just the 4 points on the rectangular grid that's around it. Okay? And I get an estimate for the potential at that point. Then given my, I'm going to do the entire calculation based upon my first assumption. At every single point, I calculate a new iteration, a new point, which is based upon the average of every single point around it. And then I do it again. And then you do it again and again. And typically within about 5 iterations, you have found the potential as a function of position throughout that entire region. Right? So a computational approach to finding the potential is really easy once you've established a program that can do that. Right? I'm going to give you, make available to you, Professor Napolitano's MATLAB program to do that for a particular situation. For homework, you're going to generalize that, not generalize, you're going to specify that to a particular problem that you're going to be assigned. And this, to be honest, is once you get out of undergraduate and graduate school, that's the only way that you solve problems. Right? Unless you're, that's about it. I think that it used to be that there were real analytical nerds who would find some way to solve it analytically, but nowadays everybody solves problems computationally. So this is the way that you're going to use later on, but we're going to spend the next 3 classes going over all the other ways. Yes?
Is it guaranteed that for any kind of geometry, that kind of iterative process will work, or are there physically real geometries where that will work? Oh,
okay. If the way that I just did this on the, it's a Cartesian grid, that's approximate. And you've got to be more careful about your averaging. But the next stage of this, which would be what a real computational physicist would do, where you're really careful about your 3-dimensional averaging, you're guaranteed to find a solution. The solution, the correct solution. It will converge. Okay.